Hello, everyone. My name is Martín Testa. I am currently working at the Institute of Material Science from Barcelona, and today I will be talking about how we can take advantage of symmetry in order to accurately quantify spin orbit torques in magnetic insulators. To this end, I will begin with a brief introduction about the origin of spin orbit torques and how we can electrically detect and quantify them. Subsequently, in the second part of the talk, I will show a novel methodology that we have developed for spin orbit torque quantification, which relies on harmonic Hall detection and macrospin simulation. And finally, this methodology will be tested on a BGIG platinum bilayer with in-plane anisotropy. And I will show you how the Joule heating induced by the injected current can actually modify the spin transparency at the interface. Well, one of the simplest spintronic devices we can think of consists of a bilayer with a heavy metal, such as platinum or any other spin orbit coupling material, and a ferro or ferrimagnet. If we inject a current into the normal metal layer, the charged current can be converted into a spin current by means of several mechanisms, such as the spin Hall effect, which happens in the bulk of the material, or the interfacial Rashba-Edelstein effect. Whichever is the origin of this spin charge conversion, since they both display exactly the same symmetry, the injection of an in-plane charge current will always result in a perpendicular spin current. If we now place a ferrimagnetic insulator next to the normal metal, when the spin current arrives here at the interface, it can transfer its angular momentum to the magnetization by means of SD exchange interactions. As a result, it will exert two distinctive types of torques onto the insulator layer, which are known as field-like and damping-like torque. The field-like torque can be thought of as an effective field that acts along the y direction, whereas the damping-like torque exhibits rotational symmetry within the XZ plane. Interestingly, it is this rotational symmetry which confers it very interesting properties, like, for instance, the capability to drive magnetization switching by electrical means. Now, how do we detect this spin orbit torque? If we opt for an electrical detection scheme, then we typically rely on the inverse spin Hall effect. As I said before, when the spin current arrives at the interface, some part of it will be absorbed by the magnetic material, while another portion will be reflected and back converted into a charged current by means of the inverse spin Hall effect. It is this extra current or additional voltage what we measure experimentally by using a standard lock-in detection technique. Experimentally, we also see that the changes in the longitudinal and the transverse resistance, they do depend on the relative orientation between the magnetization and the spin accumulation at the interface. This is known as spin Hall magnetoresistance. It can be effectively used to probe the direction of magnetization. To do so, we generally apply an AC current into the normal metal layer. This way, because of the oscillating spin orbit torques, we will induce oscillations of the magnetization about its equilibrium position. And experimentally, what we measure is the first and the second harmonic of this oscillation. The first harmonic, we can see that it is modulated by the spin Hall magnetoresistance, and it provides information about the equilibrium magnetization. On the other hand, the second harmonic is still modulated by the same SMR parameters, but provides information about the current-induced effects, such as the spin orbit torques or even thermoelectric effects. Now we know how to detect the spin orbit torques, but how do we quantify them? Well, when we are dealing with insulators with perpendicular magnetic anisotropy, we typically perform an in-plane field scan at a transverse direction with respect to the current, that is, at an azimuthal angle of phi equal 90 degrees. In this geometry, if we assume that the anomalous Hall coefficient is much smaller than the planar Hall coefficient, and also that the damping-like torque is approximately equal to the field-like torque, then we can plot the second harmonic data as a function of this of this reduced variable and then feed the data to a straight line. From this slope, then we can estimate the effective field associated to the damping-like torque. On the contrary, an alternative strategy that has been reported for in-plane magnetized systems makes use of phi angle scans. From macrospin simulations, we can see that the field-like and the damping-like torque, they display different phi symmetries. So this can be used to discriminate between these two. Thermoelectric effects, such as the anomalous Nernst effect or the spin-Seebeck effect in oxides, they will also be present, and they display a cosine phi symmetry as well. But one can easily separate between the damping-like and the thermoelectric effect by simply analyzing the external field dependence. Overall, these two methods have been widely used, even though they present some limitations regarding the accuracy of the data that we can obtain. For example, if we go back to this first strategy, we see that it does not allow to retrieve simultaneously the damping-like and the field-like torque. First, we need to go at phi equals 90 to calculate the damping-like torque, and then we switch to phi equals 0 to retrieve the field-like torque. But at this phi angle at 0 degrees, this is the geometry where the thermoelectric effects are maximized. So it will always compromise the accuracy of the data. Also, since it's particularly suitable for systems with anomalous Hall coefficient much lower than the planar Hall coefficient, then we are also restricting its applicability to insulating systems. The second strategy seems more convenient to separate spin orbit torques from thermoelectric effects, and is particularly helpful for metallic systems. But in the case of oxide systems, then we will see that the spin orbit torques are generally 2 orders of magnitude smaller than in the metallic counterpart. So a proper quantification will be more challenging. In this context, we propose a novel methodology, which is based on theta angle scans, and that will combine harmonic Hall detection jointly with macrospin simulation. This methodology will be tested on a BGG layer, 18 nanometer thick, that has been deposited onto substituted GGG substrate, and then has been covered with 4 nanometer plaque. An AFM analysis of the sample reveals that we are dealing with a root mean square roughness below 1 nanometer, but also through squid magnetometry and Monk measurement, we have corroborated that our sample presents in-plane magnetization. Before jumping onto the second harmonic measurement, we generally characterize first the first harmonic signal in order to extract some parameters that we will use afterwards in the simulation. We can see here from the first harmonic transverse resistance that it is governed by the spin Hall magnetoresistance. It has one component which is proportional to the out-of-plane magnetization, and hence this is typically referred to as anomalous Hall-like SMR. And then it also has a second term which depends on the in-plane components of the magnetization. In this context, if we perform an out-of-plane field scan, then we see a different resistance for the up and down magnetization state. And it is from this amplitude from where we can determine this anomalous Hall-like parameter. On the other hand, if we perform in-plane field scans for different phi angles, and then we plot the first harmonic as a function of the azimuthal angle, then we observe a sin to phi symmetry, from whose amplitude we can extract the spin Hall magnetoresistance parameter. Now let's move on to the macrospin simulation. Here we have the total torque that is acting onto the magnetization, which includes the contributions from the demagnetizing field, the external field, the field-like, and also the damping-like torque. Experimentally, we will rely on theta angle scans, which means that we will vary this polar angle for a fixed magnitude of the external field and for a fixed azimuthal direction of the external field. Then, for each of these theta values, we will minimize the total torque and retrieve the equilibrium configuration, from which we can extract the first and the second harmonic response. Here, I'm including the second harmonic response at an azimuthal angle of phi equals 90 degrees using the experimental parameters that we obtained from the previous slide. Also, I'm plotting separately the individual contributions from the damping-like torque, the field-like torque, and the spin-Seebeck effect, which is a thermoelectric effect common to oxide material. As we can see at phi equals 90, the spin-Seebeck effect contribution is 0. And even though they present opposite signs, we see that the damping-like and the field-like torques display a sine to phi behavior. Consequently, one cannot a priori discern between these two contributions at phi equals 90. Instead, what we can do is to go at phi equals 85 and 95 degrees. At these two angles, we can observe that the spin-Seebeck effect presents an opposite sign. This is because of the cosine phi dependence. And also that the field-like contribution is completely different at 85 and 95 degrees. However, the damping-like contribution remains practically constant. Therefore, we can exploit these differences to appropriately separate between all these three individual contributions. Here, I'm plotting the sum and the difference of the second harmonic registered at 85 and 95 degrees. When considering the sum, we still deal with the interplay between the damping-like and the field-like component. But if we consider the difference, we can see that we can effectively remove the contribution from the field-like torque. In this situation, we can easily discriminate between the field-like and the spin-Seebeck effect by simply analyzing the external field dependence. In fact, while the thermoelectric effect should remain constant for different external fields, the field-like contribution should systematically decrease because the magnetization becomes more rigidly coupled to the external field direction. Here, I'm plotting the difference of the second harmonic at 80 and 95 degrees as a function of the external field. We can observe a general decrease of the second harmonic signal, particularly noticeable here around theta equals 90 degrees, which is what I'm showing here in the close-up. This decrease in the second harmonic originates only from the field-like torque and not from the spin-Seebeck effect. So if we plot the peak amplitude registered here at theta equals 90 degrees, and we plot it as a function of the inverse of the external field, we get a linear trend. And from the corresponding slope, we can then determine the field-like torque, whereas from the intercept, we can determine the spin-Seebeck effect coefficient. At this stage, if we know the field-like and the spin-Seebeck effect component, we can now calculate the damping-like torque. And we can do this even by measuring the second harmonic at phi equals 90 degrees and then fitting the data. Or we can also go at the sum at 85 and 95 degrees. Since we already know the field-like contribution, then we can fit the data for different damping-like torques until we get the correct value. Let's move now to the experimental results. So this graph includes the second harmonic response registered from the Bigic platinum bilayer at phi equals 85 and 95 degrees. One can see that the overall shape does not match the simulation. And this is because of the occurrence of a symmetric component in addition to an anti-symmetric component. If we go back to the symmetry of our spin orbit torques and ferrimagnetic effect, we see that they are all of them anti-symmetric with respect to theta equals 180 degrees. So for further spin orbital quantification, we will only focus on the anti-symmetric component. By using the previous methodology that I just explained, these are the typical values that we obtain for the field-like, damping-like torque, and the spin-Seebeck effect coefficient. On a different side, the presence of a symmetric component can be related to in-plane temperature gradients, which are induced by Joule heating. A similar component has been reported in many other studies in the literature, and that can be thought of as the central region of the whole bar being warmer. Aiming to shed some light on this thermal effect, we have measured the second harmonic at phi equals 90 degrees as a function of the current. And contrary to the linear behavior expected, we can observe deviation. We can observe deviations from linearity at high current density, where moderate Joule heating is anticipated to occur. We have also checked the current dependence of the SMR related parameters, and the results are depicted here in this graph. What we see is that whereas the anomalous Hall-like coefficient in black color is seen to slightly increase along with the current density, the spin Hall magnetoresistance, we see that it decreases dramatically and more significantly above this threshold from which deviations from linearity were previously observed here in the second harmonic response. So this fact, really points to the modulation of the spin transparency at the interface by in-plane temperature gradients and Joule heat. This is further confirmed here in this graph, where we are plotting the variation of the damping-like torque and the spin Hall magnetoresistance parameter after normalizing over these values, which were obtained where no Joule heating is expected. The variation in both of these two parameters is seen to correlate pretty well. So this confirms that the modulation of the second harmonic response here at high current densities is strongly influenced by the Joule heating. To sum up, through this study, I have presented a novel methodology that allows to quantify the spin orbit torques without an important interference from the spurious thermoelectric effect. And for that, we simply consider an alternative geometry at phi equals 85 and 95 degrees. This is seen to result, in an error in the damping-like torque as small as 0.2%. And also compared to other methods from the literature, like the one that I showed in the introduction, our methodology allows to retrieve simultaneously the field-like and the damping-like contributions. And also, we have found that this methodology is even stable against a small phi angle misalignment. And finally, I have also shown the implications of in-plane temperature gradients induced by Joule heating, which strongly modulate the spin Hall magnetoresistance parameters and will influence as well the second harmonic response that we measure. And this is all on my side. So many thanks for your attention. Bye-bye.